All right, so that's line angle to Newman, Newman to line angle. I think the last thing we really want to talk about in the past chapter would be the chair conformers, and I think we're pretty good at that. So we're going to draw both chair conformers, and this is kind of how I would always do it. So I'm just going to pick the top one to be 1 for fun. I don't really know why. I'm just going to pick that as such. And I'm going to draw my first chair conformer where carbon 1 is being pulled up and carbon 4 is being pulled down. Okay, so if carbon 1 is being pulled up and above the plane, then the stereochemistry of that constituent most definitely wants to be up. Does that align with my trend? Yeah, so I see that wedge. Wedges like to be up according to what I said. So I'm going to draw this actually the right way. Okay, and then on 2, it says it should be on the dash, which means it's down. Okay, it typically likes to be down. And does my trend allow for it to be down? Well, yeah, because we know it's up, down, up, down, up, down. So yep, we're supposed to be down. So if it matches my trend, we said that has to be axial. Okay, and what COOET is the ester version. Okay, the ester, not OH, but OET, the ester. Okay, and ET could have just been also abbreviated as 2 carbons, ethyl. Okay, so this would be chair conformer number 1. And you know, clearly I see I have an axial substituent above here. So I have an axial here, and I have an axial down here. And in my next chair conformer, I know both of those have to be equatorial. So in my next chair conformer, okay, so now this is still 4, so 1. Okay, so 1, that carboxylic acid was axial up. It has to be equatorial. And that proton, this hydrogen, which was equatorial, is now axial down. And then on 2, that ester, you know, this ester was axial down, and it needs to be equatorial now. So let's draw it like maybe this. And then axial up would be that proton. Okay, so you know, clearly I think you guys should be able to rationalize real quick which chair conformer is more stable, and it's definitely the one on the right, structure B, because we don't have these 1, 3 diaxial interactions on the top, and we don't have the 1, 3 diaxial interactions on the bottom. Okay, we kind of minimize those. So again, this is kind of like a brief summary of like that whole last chapter of what we did. You should be able to know how to go from a Newman to line angle, from a line angle to Newman, and also know how to do these chair conformers and rationalizing their stability. Okay, so this is the most important things from the last chapter. Anybody have any questions on anything before we move on to new material? Cool. All right, so we're going to move on to chirality. So chirality, weird thing. So a lot of you guys probably have never seen chirality before this class, and you've actually seen it every single day of your life before then. And it's, if you put your 2 hands out, why do I not have, like, you know, the exact same hands? Like, we have symmetry, but we don't have the exact same objects. And how do I know I don't have the exact same object? Well, there is no way that I can rotate one hand and get it to be the exact picture, you know, with my nails on top. Like, there's no way. I can flip it like this, but I can't get the exact same mirror image. And that's called chirality. And what that means is, like, it was built differently, essentially. So like, well, a lot of people get this confused and they think they're like all the exact same thing, just mirror images, and they're not. It's like, this was, my right hand was built completely different than my left hand was. And it's like the same thing with a molecule. So like, let me just draw this example. Like, so let me do, and let me draw, you know, let me draw its mirror image. Actually, I'm gonna do it like this. Okay, so essentially I just made some random tetrahedral carbon, okay, with 4 different substituents. And you know, they look similar, like they look like they're the same. And the thing is that they're not. And the reason that is I literally, you can just imagine that I made this carbon bromine bond, I stuck it on the front. And then on this structure, I stuck it on the back. And then this carbon chlorine bond is on the back here, but I stuck it on the front here. And these aren't related via rotation. There's no way that I can, turn this around and plop it back on there. And the reason that is I quite literally built it differently. I built these bonds differently in the structure. And that's what's going on with your hands. Like your hand was built, in a certain way, and your left hand was built in a certain way. And even though they're mirror images, they're not the same. Okay. So that's kind of like the whole concept of chirality. So the first thing I want to do is just like figure out how to identify a chiral center. And this is what you always look for. So number one, ID chiral centers. So chiral centers. You have to look for an sp3 carbon with 4 different substituents. Okay, so there are other chiral centers that exist in the fields of chemistry, specifically in inorganic. There's a whole bunch of different criteria, but for organic chemistry only, it's going to be an sp3 carbon with 4 different substituents, and they have to be all different. Okay, so I'm going to copy down, this is 1C if you guys are following along in the student workbook. And I'm going to draw this real quick. And we have, it looks like this one, we have, sorry about this, I wish my printer was working. I think that's it. Yeah. So we want to look for the chiral centers in this structure. So we're essentially just looking for any carbon that is sp3 hybridized and it has 4 different substituents. So let's start here. So first of all, this carbon, what is the hybridization of this carbon? Well, if you're thinking sp2, it's correct. It's not sp3 because I have 3 total areas of electron density, this double bond, this single bond, that's 3 areas. So this cannot be a chiral center. This carbon, yeah, it's definitely sp3. I know there's 2 hydrogens there, but it's not 4 different substituents because there are 2 hydrogens, so that can't be chiral. And the same thing with these carbons. These can't be chiral because they have 2 protons or 3 protons. Same thing for this one, there's 2 protons, same thing for here. So anything, in typical line angle is not going to be a chiral center because they have more than 1 proton and you need 4 different substituents, okay? So then if you look at, maybe this carbon has, this whole group, this oxygen group, whatever, ether to the left. Okay, it has the right side of the ring, it has the bottom part of the ring, and it has this hydrogen. So yeah, that seems like it's 4 different substituents. So quite quickly, you're just looking for, do I see 4 different things connected? And yeah, I see 4 different things connected. So this is definitely sp3, 4 different things, and that's the first chiral center I see. Okay, so again, for this one, I see I have this amide coming off on the wedge. I see I have a proton on a dash. I see I have this like left fragment of the ring. So I'm just like looking at the left side is different from the right side. So yeah, that's 4 different things attached to that one carbon. So this would be a chiral center and this one would be a chiral center. Okay. And then finally, this one is also going to be a chiral center because we have that amine going on the dash. We have that proton on a wedge. We have this right side of the ring with this ester, and we have this left side of the ring with this ether. So yeah, that's 4 different substituents on that carbon. So those are my 3 chiral centers, okay? So it's pretty easy to identify them. It's just looking for sp3 centers, okay? And each one of those substituents has to be different. So you basically look for the complicated things, essentially. Look for the complicated functional groups in there. That's a big hint. Let's do one more example. So we're gonna do 1D, why not? I'm gonna copy this for a second, 1D. So here we have this, we have that, yeah, this. And something down here. And some other crazy things going on. Okay, so we have again, I really apologize about this. Normally it's not this slow. Okay, so here we are. So we have this structure. And what you want to do is, again, look for those sp3 centers where each one of those is going to be a different substituent. So I'm just going to start from down here. So I don't really see, first of all, this is definitely going to be an sp3 nitrogen. Well, actually, that's not true because of resonance. But if this double bond wasn't there, we would think that this would be an sp3 nitrogen. But again, the criteria specifically for carbons, okay, it has to be an sp3 carbon with 4 different substituents. So don't look for nitrogens or other atoms, okay? It's always going to be carbon. So clearly nothing going on here, okay? Here I see another carbon, but it's not 4 different substituents, even with this hydrogen, because we have this left side is the same as this right side. Okay, the left side of this ring on this side is the same as the right side. So, you know, for all intents and purposes, those are the same things and they're not different. So no, this one doesn't work either. This is a benzene ring, and benzene is never chiral because it's all sp2, so no. Okay, so now we're over here. So I see this carbon, okay, right here. Yeah, it looks like that could kind of work. It looks like I have this whole right crazy looking benzene thing. I have a hydrogen. I have this left thing with a pi bond close by, and then I have this right thing, and that's different. So yeah, that works. This definitely works. Remember what I said? This doesn't work because those have 2 protons. This doesn't work because it's sp2, sp2, sp2. None of those are working. Here, this doesn't work because the 2 protons. So you can see, like, you can really eliminate a lot of these. Like, they're not all going to be chiral. Then down here, so can't be this one, can't be this one, can't be this one, can't be that one, because those all have more than 1 proton. It can't be the nitrogen, can't be this nitrogen. So it looks like I have 2 more chiral centers in this one and this one, okay? And why does this work? Because we have this, you know, ethyl alcohol coming up here. We have this right top of the ring. We have a hydrogen you don't see, and we have this kind of chlorine group going down. And you kind of rationalize the same thing for this chlorine guy right here. There's this chlorine, this right thing, this up thing, and this hydrogen, okay? So I think that's pretty good practice. Charles, I think you have your hand raised. You don't have to raise your hand. You can just kind of say it out loud, whatever you want.
Yeah, no, I just had a question on the identification of the first carbon there.
Yeah.
So the 4 different unique substituents we're looking at: the benzene, the sp3 carbon and sp2 carbon, and the hydrogen. Those
Yep.
are why it's all unique.
Exactly. Perfect.
Gotcha. All right. Thank you.
Yeah. So again, just taking off of what he just said, that's actually really good terminology. This is an sp3 carbon. This is an sp2 carbon. This is the hydrogen, and then the benzene. So that's kind of, those are like the professional terms that he was saying. So we're comparing on this carbon, the sp2, the sp3, the benzene, and the hydrogen. And all 4 of those things are not the same. So that's clearly why that was a chiral center. Great question.
Steven?
Yeah, what's up?
So you see the carbon that's connected to like the butyl group and then the amine and then the N?
Butyl group. Right here, something like that? Talking about this one?
Yeah, what about that one?
Yeah, that works. I didn't see that one before. Yeah, that totally works. Great find. I love that one. All right. So again, why does that one work? So we have this butyl group coming off. So this is the butyl group. We have this nitrogen, you know, up here. And even though we have a nitrogen coming over here, it becomes different later on. You can see like it's nitrogen, but then it becomes this ethyl alcohol, and it's nitrogen, and this becomes chloral. So people tend to make these a lot harder than they are. You just quickly look at it and you just see like, are they different? And the biggest like hint for that is like there's no symmetry. Like if you don't see symmetry, it's not the same. So pretty good idea that it's going to be different substituents or chiral. And I think there's some questions in here. What about the other carbon in the ring? Oh yeah, I think. What about the other carbon? Yeah, I think we answered those. Okay, so that's it for chiral. I think somebody has a question. Yeah.
For one, I think I don't know if it applies to specifically 1A and 1B, but if you look at those, you can kind of see what I'm talking about. I don't know if you have it next.
Yeah, I do. What are you talking about?
So, you know, so if we're like looking for a chiral center in a ring and we're trying to go down either side, but there's also another ring attached, like if it wasn't benzene, like do we go into the other ring? Like, I don't know if that question makes sense.
Yeah, no, it totally does. So you're saying this. You're saying something like,
I don't know if you know, like there was a question that had like morphine as the example, like the structure of morphine. But
do you have it and you want to share your screen or something like that?
I mean, I can find it and share my screen if you'd like.
Yeah, let me know and we can take a look at it when you pull it up and share your screen and whatnot. Sounds good?
Yeah, I have it if that's okay.
Oh yeah, do it right now. Let me see if you have sharing options. Okay, try that.
Okay. So that's a different molecule actually, but I will, this one?
Yeah, looks like it.
Okay.
Okay, so you're trying to say, like, when you're looking for chiral carbon atoms in rings, do you go into the other ring, essentially?
Yeah.
Yeah, and that's true. That is exactly true. So let's kind of just look at, can you put your mouse over, so you see that ether? And go to the carbon right below it. One down. Yeah, right there. So everybody's kind of following us on where we are. We're on this morphine structure. Look at Caroline's mouse. So it's right there where that wedge hydrogen is. Okay, so when you're trying to like determine if that carbon is chiral, well, just look what's immediately attached to it. So I see I have a hydrogen to my left. I have the oxygen going right up. Okay, and then I have a carbon going down into that ring. Okay, that other ring. So that's something. And then a carbon across. And that's into some other weird, crazy ring. Like, those are clearly 4 different things, like, you know, and that's exactly how I would do it. So you do go into these other rings to check for point of differences, but like, it's so obvious, like, you know, a lot of these are very obvious. So now where Caroline's mouse is, so like, let's just talk about that one. So we have, you know, the left kind of group. So if you just, can you drag your, that whole group right there, yeah. And then you have this right whole group, which is a completely different ring with the nitrogen kind of in there. You have the top thing, which is a whole nother thing. And then you have this like wedge thing coming out. So you're literally looking for 4 completely different things. And this molecule has a lot of chiral centers. Is everybody kind of good on that?
So like, if we're looking at this one, you wouldn't just look here and say like, oh, this is a carbon with this hydrogen, and this is also a carbon with this hydrogen. Like, those aren't the same.
So yeah, so that's how Dr. Peterson and Dr. Habenik teach it, where they're like, you count each atom. Like, you don't necessarily have to go that tedious. You can just like look broadly, are they different? And they are. You see that? They're so broadly different where like this whole right ring with the nitrogen is completely doesn't, like the other ring on the left doesn't have a nitrogen, and the thing on top doesn't have a nitrogen. You see it? See what I'm saying? They're all very different.
So like, it goes into here, like you would.
Yeah, it's the whole thing. Yeah, it's that whole group is what you're kind of referencing, if that makes sense.
Okay, cool. Thanks.
Yeah, you'll get better with like practice. You'll see like what you can do, your shortcuts. But yeah, it's just very, very, to me, it's very obvious. It's just 4 different things attached. All right. Yeah, I think that's good on this stuff. Let's move on to determining chiral, achiral, and meso. So we're on question 2 on page 40 still. And this is a really important skill. Okay, I got some questions in here. Sorry, David. So could we look at stuff like sp3 and sp2 the same in terms of like primary, secondary, etc. carbons? Can you elaborate, David, a little bit more?
Yeah. Sorry, I didn't read that well. So basically, like when like determining different substituents, right? He said like this one's different because it's sp2 and this one's sp3.
Yep.
Like that, you could be looking at that the same way. Like this one's different because it's a primary carbon, for example, or this one's different because it's a secondary carbon.
Yeah, that works. You can use literally anything, and that's totally fine. Yeah.
Okay.
Because they're not the same. That's really what it is. It comes down to yeah.
All right.
Yeah, Lauren, could you have a chiral center with a carbonation? Do you mean carbocation? Is that what you mean? Carbocation?
Yeah, that's what I mean.
Like a carbon with a lone pair. I guess with lone pair. No. At least no. That center could be sp3 with the lone pair. So like basically, you could have something like this. Like this is an sp3 carbon because we know that there's another proton there. That's an sp3 carbon with this lone pair, but it's not chiral because you need 4 substituents, and a lone pair is not a substituent, from what I know. Okay, that's a good question though. Charles, so we don't need to identify hybridization. Just yeah. You don't need to do the hybridization. You did that, which was great in that original example, telling me that this is sp3 and sp2. But no, it has nothing to do with that. It's basically just very like macroscopically what looks different. Like, are there 4 different things? Yep, and that's it. Yep, cool. All right, let's move on to, how to know, this is question 2, whether something is chiral, achiral, or meso. So just because a molecule will have a chiral center, or at least one chiral center, it doesn't mean that it's overall chiral, okay? So that's a very important thing to know. Just because something has chiral centers doesn't mean that it's a chiral molecule. Okay, just like when we said earlier, just because a molecule will have a polar bond, which means that there's a dipole, doesn't mean that the overall molecule is going to have a dipole moment. Basically, an example of that was this. Remember this example? We saw that in this tetrafluoro, carbon tetrafluoride structure, we see that we have localized dipoles towards all of these bonds. So there are dipole moments in there, correct? But the overall dipole moment of this molecule is going to be 0. Okay? So it's the same concept with chirality. Just because some things are chiral in it doesn't necessarily mean that the whole thing is chiral. Okay? So let's take an example of this. So we're on 2A, and these should be easier to draw. So we're here, here, and here. So the question is, the first thing that you need to do is identify any chiral centers. And quickly, in the chat box, everyone write yes or no, are there chiral centers in here? Okay, Abby says no. Anybody else? Roxana, no. Okay, keep going. No. Great, yep, no. So the answer is no. Any of these like carbons are not going to be chiral centers because they're CH3s and CH2s. No, I like the all caps. It means you're confident. So any of these are not going to be chiral because they're more than one proton. And that's the kind of the obvious like eliminating. There's more than one proton, so that's not the same. And then here, these aren't because they both have methyl groups attached to them. And then here, this one isn't a chiral center because the right isopropyl group overall is the same as the left isopropyl group. So there are absolutely no chiral centers. So when there are 0 chiral centers, hopefully you guys are understanding my tech language. When there are 0 chiral centers, we can say achiral every time. Okay? If there are 0 chiral centers and at all, it's always going to be an achiral structure. All right, so are we kind of good on that so far? That obviously makes sense. If there's not a single chiral atom in there, the molecule overall will not be chiral. I think that's kind of obvious. Okay, so 2B. So 2B looks like this. Okay. That's a new language. Yeah, right. New language. So we're here. So we have, I think, did I draw one more? Yeah. So we have a chlorine going up, and we have this, ketone going down. So do I have chiral atoms in here? Again, yes or no? Be careful. Caught some people. Yes. Wait, I love that. Yeah, so the answer is yes. So this was a little trickier. So we do have chiral centers in here. So if we definitely know it's not these. We definitely know it's not these. We definitely know it's not that one because that's an sp2 center. But these carbon atoms that bear the chlorines, these are chiral. And the reason they're chiral is because we have, look, we have these ethyl group to my right. We have the chlorine, on this dash. We have the hydrogen not drawn in. And we have a ketone immediately next door. So like clearly that's 4 different things. Like, so we have a chiral center here and a chiral center here, like 100%. But is this molecule overall, is this a chiral molecule? Okay, and maybe put that in the chat box. Is this molecule overall chiral? No. Okay, so good, no. So essentially why? And we need to understand that. So when there are chiral centers, okay, so the first thing is 1, ID chiral centers. Number 2, then you check for sigma planes. And what is a sigma plane? Okay, that's the next thing. So we first identified the chiral centers. Then we need to check for this something called the sigma plane. And sigma just comes from S, like symmetry plane. Like, I don't know why they call it symmetry plane. I mean, a sigma plane, I would just call it S plane, but whatever. So sigma plane just means symmetry plane. And is there symmetry in this molecule? Yeah, 100% symmetry. So that's what they call a sigma plane for some reason. Okay, and when there is symmetry in a molecule with chiral centers, it's achiral as well. Okay, so let's write that next rule. When there are chiral centers, but also a sigma plane, you get achiral as well. Okay, so these are the 2 instances that we can get achiral. Okay, so one where there are no chiral centers, or one where there are chiral centers, but there is symmetry. Ayana, you just beat me to it. I was just going to get there. And I was like, but wait, is there one more term that you can give it? No, you're good. Is there one more, name that I can give to this structure? It just means you're on top of it. Don't be sorry. It's awesome. So yeah, is there one more name you can give to this? And yes, so there is one more additional name that we can call this besides being achiral, and it's called meso. And meso is reserved exclusively. Some people always say like meso or something like that. It's meso compounds, okay? And what does meso mean? It basically just means it's miso soup, right? It's basically like the, it's a molecule, okay? That when you have chiral centers in it, because of the symmetry around those chiral centers, nothing is gonna happen, okay? And we don't really know what that happen thing is yet, but I'm alluding to rotating light. I don't know if some of you guys know that yet, but essentially, because of the symmetry, whatever this chiral center is going to do, let's say rotate light maybe this way, and whatever this one's going to do is going to rotate the opposite way. So you can see the same thing with the dipoles. This rotation cancels with that rotation, and we get overall a chiral. And we just give it this name meso, kind of just like how we gave, you know, the anti-conformation, that conformation, sorry, that was so bad. The specific conformation that's known as the anti-conformation gets that specific name in addition to being known as the staggered conformer. It's basically the same thing, okay? So that's 2A and 2B. Let's keep going. So 2C. So 2C looks like this. And I think this is our final rule. And I think that's it for chirality. So first thing, identify chiral centers. Nope, 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 nope. Okay. Oh, you can't see? Sorry about that. So nope, 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 nope. And then finally, we're left with this one, and we have a chiral center. How do I know that we have a chiral center? Well, we have an ethyl group to my right. We have an isopropyl group going to my left. We have the hydroxyl group going down, and we have the hydrogen over here, okay? So notice, I don't do, no. Say that backwards. Say that exact phrase backward. So it would be, achiral doesn't always mean meso, but meso always means achiral. That's true, okay? Because you could, again, back to that example of where we had no chiral centers, that was considered achiral, but not meso. Let me go back to that. That's actually important. Like here, we had 0 chiral centers, but that wasn't called meso. Here, we had chiral centers, and it's called meso, okay? But both are achiral. That's important. Meso is a specific type of achiral. I love that. Whoever just said that, let me see. Yeah, Abby, that's great. Meso is a specific type of achiral. That's exactly what it is. Wait, could you explain the sigma plane again? Dumb it down. I don't really know how much dumber I can make it. It's just like sigma plane means symmetry. Do you see symmetry? That's basically it. And if there is symmetry, then like it's achiral. That's it. There's no chiral atoms and no sigma planes consist of chiral. No, Andrea, that's not true. You have to have at least one chiral center for it to be chiral, and we'll see that right now. Okay, so back to 2C, and I can go back to these questions in a second. Back to 2C, this is our chiral center right here, okay? And there's only one chiral center, so our last rule is that there's one chiral center, one or more, I should say, 1 plus chiral centers, and no sigma plane, it's always going to be chiral. Okay, so those are our 3 rules. So if there are no chiral centers at all, achiral. If there are chiral centers and there's symmetry, it's achiral / meso. And if there is chiral centers and no symmetry, it's chiral. And I think that all logically should make sense to you guys. Okay, let me just check some of these questions again. So 2B is meso, but also achiral, but the answer is meso. I see what you're saying. I put both. I never. Okay, I see what you're saying, Charles. So essentially, everybody listen. If you're zoning out, whatever, on the test, you need to give the most specific name possible. So Charles is great for saying this question. Like, you need to say meso for that last example. Okay, it's right that it's achiral, but the real specific name is meso. It's just like if you were to say, like, what's the name of this Newman projection? And you could say it's the staggered conformer. But we really want to know, do you know what the anti-conformation is? You need to give us anti-conformation, if that makes sense. You want to give the most specific name as possible, okay? Great, that's actually a good point. Andrea, if you want to find that problem and share your screen when you get the chance, that'd be great. Okay, so that's 2C. And then let's do 2D real quick. Okay, so I think you guys are getting faster, obviously, at these. It takes a little bit at first when you're just first looking at it, but I think it's not too bad.
Wait, I have the problem in my notes. Can I just like share it on my camera?
Sure, yeah, if you can get that on there.
I don't know if you guys are gonna be able to see it.
Let me see.
One with, I don't know what I'm showing.
I see. So you're looking at
The one with the dot in the middle?
Yeah, so she's talking about the carbon. So she's just talking about sigma planes here purely. Yeah, so I know what that means. It looks like this. I'm gonna draw it down here. I think she's drawing something like this. Like this, you know, let me pin this video. Like this alkene, okay? And it's just tetrasubstitute, meaning there's a methyl, 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 methyl. And where are the sigma planes in this? So I see two symmetrical planes. Actually, I see more. I see three. No, four. I think I see infinite. I see infinity.
But she
No,
kind of explains that since
Yeah.
it's sp hybridized, then there's like they're on different planes because the p orbitals are perpendicular. I don't know. Like she kind of confused me, but she said it was a chiral molecule.
Yeah, this is chiral for a different reason. We're not there yet, so maybe wait till the end of this talk, because we'll get to chiral centers that aren't sp3. But essentially, it has something to do with like the geometricness of this geometric, and it has something to do with cis trans, and that's at the end. We'll talk about it at the end. I promise I'll get to you. Okay.
Thank you.
Yep. So we're here. So essentially, do I see chiral centers? Yep, I see one here. I see one here. I think you guys can identify those by now. Is there symmetry? No. Chiral. Done. Like, don't make it any harder than it has to be. Okay? Yeah, Abby, you're great. Thank you for always like answering people's questions, like, and you clearly know your stuff. So great job there. 2E. So we have this structure. And okay, so we're at the structure, all right? And we see I have two chiral centers. I think you guys are quick at these by now. Okay, but is there symmetry? Okay, everyone in the chat box, is there symmetry? Yes or no? Yes, 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 yes. Okay, the answer is no. The answer is no. Okay, there you go, Ayana. Their answer is no. So for symmetry purposes, it has to be the exact same stereochemistry. Yikes. No, it's good though. I'm happy you guys made this mistake now, because then you won't do it again. So clearly, because they're both not wedges, there's not really this plane in the middle. Like this is oriented towards the back, this is oriented to the front, so it's not really symmetrical. So for all intents and purposes, there are chiral centers and no sigma planes, so this makes it chiral. Okay. Okay. It's with respect to this in the middle, and there's no symmetry. Does that make the middle carbon chiral? No. So again, the middle carbon would be sp2, and you have to be sp3, remember. Cool, great. Seems like we're good. Red. Everyone's like red. All right, 2F. So this is a trick, and I'm just gonna say that off the bat. And this is a very common trick that a lot of people do.
Steven,
Okay.
can I ask you a question quick?
Sure.
Just to clarify for the last one, if they had been the same stereochemistry, it would have been meso, right?
Exactly. Yep.
Okay, thank
You
you.
got it. Everybody listen to what we just heard. So essentially, if this was a wedge or if this one was a dash, they are still chiral centers, but now with the sigma plane. So that makes it achiral, and more specifically, it makes it meso. Cool. So that's great. Those are all the things that you need to like know from this. Cool. So a very common trick, and obviously pay attention to this, is we'll give you wedge dash orientation, because people sometimes are careless and they'll just go right to circling this. Okay. And you're right to go there. Like that's definitely a good idea. You always want to go to the wedge dash things, because that typically indicates sp3. But in this case, you see we have a propyl group to my left and a propyl group to my right. So it's really not a chiral center like we think it is. So this is no chiral centers, so that makes it achiral. Okay. I don't really think these are too bad. I don't know what you guys are thinking. Okay, so 2G, and we're here. So we have this structure. So this is another important thing we need to discuss. SH and SH. Okay. So first thing is identify these chiral centers. So, okay, no. Okay, I have an ethyl. I have to go a little bit careful. I have two carbons to my right. I have this 1, 2, 3 carbon with this sulfhydryl to my left. I have the actual sulfhydryl, and then I have the hydrogen. So yep, that's a chiral center, and that's a chiral center. Okay. Is there a sigma plane? Okay. Anybody see a sigma plane? Anybody see a sigma plane? Chat box, yes, no? No, great. I don't see one. I don't see one either. I don't see one. Oh no. Okay. But there's something I need to do, okay? And this is like, you guys are gonna hate me for this. You always have to just check subtly if there's a rotation possible. Okay, so I'm gonna rotate around this carbon-carbon bond where those two sulfhydryl groups are. And essentially, I'm gonna get a structure that looks like this. If you can't see that, I'll explain it. So this is my right side. So if you can't see, I'm basically doing from right to left, okay? And this is the carbon that's here. This is the carbon that's here. And this is the sulfhydryl group that was already on a wedge, okay? Whenever you rotate around a bond, so this was trans and now it's cis, this dash thing, which was into my paper, so quite literally like, how can I depict this to you guys? Maybe like, gotcha. Okay, so see, like the red pen would be like a wedge, okay, coming out, and the black pen is the dash. So when you were to rotate it 180 degrees upwards, or keep in mind this is the black pen going into the paper, it now kind of sticks up and out, okay? So you should just know that the dash becomes the wedge and the wedge becomes the dash when you rotate. So this dashed sulfhydryl group is now on the wedge orientation. Okay, so you guys see that? Okay. So when you rotate, okay, so all I'm doing is rotating and pulling it up into space. Now I see the sigma plane, okay? So even though in this kind of structure, we didn't see the sigma plane, it really is there. So this would be a chiral molecule, and more specifically, it would be meso. So this is definitely one of the harder ones. Abby, you did know it had a sigma plane. I know. Okay, so let's go back to these. I did see you were like one of the only few people that saw it in the beginning. So yeah, so at first you're right. There really was no sigma plane that I saw, but upon rotation, that's when it came about. So let me read these questions. I thought chiral centers must have 4 different substituents, but there are 2 sulfhydryl groups. So no. So it's with respect to each carbon. I think that's the issue there. Oh yeah, you have to look at the entire substituent. I see, Kelsey. Oh, you guys answered it. I didn't get there. All right, thank you guys. How did we know how to rotate? It's very obvious to rotate when you have 2 adjacent functional groups that are the exact same thing but opposite stereochem. Do you guys follow that whole phrase that I just said? This is a huge, this only happened, like I only thought to rotate because this is a possibility. Like, and it's only a possibility if you have like 2 of the same things that look pretty symmetrical and like opposite stereochem. That's the only reason why I'd rotate in the first place, is to see if they would get to this form. So some atoms in trans check for rotation. Perfect, Lauren. Love that. Love that. That's great. Check for rotation always. But it's specific. You don't have to check for always every trans one. You only need to check for the ones that look pretty similar. Okay? Like, I don't know. Maybe that helps you guys. And I think we'll get some more examples of that. So let's look at 2H. And this is a perfect example of when not to rotate, when you don't need to. Okay, so it's kind of, it looks like the same thing, okay? But the only thing that I changed is I think I added this extra methyl group, okay? Yeah, Caroline, what's your question for G?
So like one thing I kind of do sometimes is like try to do with my hands, but like if you rotate, like for the dial it's going outwards, like towards the paper, like if you rotate that like upwards, wouldn't it still be going out or no?
No, it would stick out in the plane, and I have to show you this in a better way. Let me see if I have something. Here, give me one sec. That's actually a very important thing that you should see. So here, let me just show you this model for a second. And okay, so here, so this is basically like you looking at the carbon, okay, like this. So this would be like line angle structure. Okay, and the purple ball is going to be sulfhydryl, okay? So that's this dash sulfhydryl, and the green is the hydrogen, okay? So see how the purple is into the plane, that's the dash, and the green is gonna be the hydrogen. So now I'm gonna rotate that upwards, ready? So remember, keep in mind the sulfhydryl is the purple, so rotating this up. Now the hydrogen is in the plane, dashed, and the purple sulfhydryl is out. So I'll do that again. You're rotating it up. 180 degrees. Now it's out as a wedge. Before it was a dash. Now it's a wedge. Do you guys see that? Maybe? Perfect. Okay. So yeah. It would be on a wedge, not a dash. All right, let me keep moving. Good. I hope that helps some things, some people. Okay. So let's do, so 2H. Why don't I have to think about rotation? And the only thing that I changed was adding this extra methyl group. And the reason that is like, it's not going to be symmetrical. Like you can see with respect to like maybe this bond, you have 2 carbons to the left and you have 3 carbons to the right. So even if I were to rotate it, which would look like this, like, where's my black pen? It would be, do you see, it's still not symmetrical, okay? So it's kind of obvious, like, when to know to rotate, and it's when you have 2 very similar things, opposite stereochemistry, and it's pretty darn symmetrical on both sides. There's 2 carbons on the left, 2 carbons on the right, okay? Here, there was no reason to do that, okay? We're trying to do this smarter, not harder, everybody. All right. 2I, okay, so 2I. So 2I looks like this. And I think I'm going to stop here after this one. OH. So, oh, I'm sorry, I didn't even answer that question. So no, for 2H, there is chiral centers. There is no plane of symmetry, so it should be chiral, actually. Chiral. Somebody have a question? I think I hear mic muted. Okay. So 2I. So I see right here that I don't have really any chiral centers. Do you guys see chiral centers? Nope, achiral. All right, I think we did enough of that. So pretty much you know how to identify chiral centers. You know how to classify a molecule as chiral, achiral, or meso, or meso. And then the next thing we need to do is absolute configuration, all right? So we're gonna go to absolute configuration. So here we are. We have, hope she gives us 10 of these positive exams. Okay, so good. I think that means you feel good about that. That's awesome. Yeah, this is definitely going to be all over your test. So the first thing is we're going to do this now. So I do this, again, a different way than most people get taught it, but I don't know, whatever. Do with that what you will. And so we do something called Kahn-Ingold pre-log rules. And it's just really, honestly, to me, I think it's so easy. Like, you just look for this structure, we're going to look for complexity, okay? So whatever substituent is the more complex, meaning more carbons, more hydrogens, more atoms, period, is going to be a higher priority, okay? And that should just kind of make sense. Everything here we're dealing with is just carbons and hydrogens. So the highest priority for this example is going to be given to the largest, bulkiest, craziest substituent. So out of the methyl, ethyl, and propyl, or hydrogen, which one is the highest priority? Methyl, ethyl, propyl, or hydrogen? Put it in the chat. Ooh. Okay, I'm seeing some methyls and ethyls in the beginning. It should be propyl. Okay, so again, it's just the most complex. So it's just, didn't hear the options. So it would just be the most complex. So again, clearly, 3 carbons is crazier than 2 and 1, or a hydrogen. So 4. Or no, sorry, 4 is the lowest. My bad. I'm sorry. 1. 1 means highest priority. Okay. What's the next one? Clearly the ethyl. 2. What's the next one? Clearly the methyl. 3. What's the next one? Hydrogen. 4. Like, it's that easy. Like, I don't think it's any harder than that. Okay. So quickly, you just have to assign 1, 2, 3, and 4 to these priorities. Okay. I don't do CHH, CHH thing. You know, I don't do that. It takes too long for me. So quite literally, just look for complexity. 1, 2, 3, 4. And then now you have to trace this, okay? So by tracing it, you go from 1 to this 2 to the 3. Okay, what was that arrow? So is that clockwise or counterclockwise? Counterclockwise, right? Counterclockwise, good, counter. So the only way that I memorize this is, see Abby, so the only way that I remember this is that anything towards clockwise, so clockwise would be the opposite way, is towards my right. Like, you're drawing that towards my right, so that's always R. And then the other one is always S, okay? So R and S, okay? So clearly this matches the other one. It's not to the right, it's to the left. And the left I always know is S. So this is an S configuration. We don't know what R means. We don't really know what S means. We just classify them as such. Yeah. We can go into a little bit more theory if you want, but who cares for now? Okay, so the point is just number these in terms of priority and then assign R and S. Okay, So I'm not going to go to B yet. I want to do that last, and I'm not going to do, actually no, B's good. I can do B for now. So this is B, so it looks like this, in a chair, and we're talking in a ring, so here, and we're talking here. So we want to number these substituents now. Okay, so now when there isn't just all carbons, you have to look at the identity of those atoms. So the identity of the atom is going to be dependent on like the atomic number, obviously. So the more protons you have, meaning the higher your atomic number is, the higher priority. So honestly, like all those heavy metals, lanthanide, actinides, we're not going to see those, but those would be the highest number. Okay, those would be the highest priority because they have the highest amount of protons. Okay, so quickly, when we're looking at this structure, I see that I have, and we're talking about this chiral center, immediately a fluorine and a hydrogen, and then the rest are carbons. Okay, so between fluorine, carbons, hydrogens, whatever, it's pretty obvious that this is going to be number 1, this is going to be number 4, and then I have to look a little bit closer at what's 2 and 3. Does that make sense? It's just atomic number now. Fluorine is clearly the highest, hydrogen is clearly the lowest, and then out of the next 2, which are carbons and carbons, those are the same. So I have to look a little bit closer. From the left side of the ring versus the right side of the ring, which one is more complicated? In the chat box. Right, yep, right is right. Yeah, so right is clearly more complicated. It has an extra hydroxyl group. 3, I keep getting this numbering backwards. 2, 3. Okay, 2 is the second highest priority, then 3. Okay, it's that easy. Like it's just, I don't know. So then trace that. So 1, 2, 3. So that's 1, 2, 3. That kind of looks like I'm going towards the right. So that would be R. What is the R and S thing? So it's just how you trace it. So yes, as long as you know how to number it, that's half the battle. 1, 2, 3, and 4. The next thing you have to do is trace those numbers. So how do I trace those numbers? I'm sorry, I probably didn't say that in the first. Imagine you're driving a car, okay? You're driving your steering wheel, all right? And your substituents are quite literally like your left hand, your right hand, and let's just say like your head. I don't know, your left hand, your right hand, your head. Those are your 1, 2, and 3. Okay, and then 4 is going to be the steering wheel. So the rod. So the rod, I don't really know how to do this, but see if you have to leave. Yep, this is my steering wheel from a side view. So my left hand may be 1, my right hand might be 2, then my head might be 3, and the like I guess cylinder that it sits on is 4. And that's exactly how you want to trace these orientations. It's like once you have 1, 2, 3, and 4, you are going to look at it in such a way where 4 is oriented away, okay, so in this kind of steering rod kind of orientation, and you're going to hold 1, 2, and 3. And if you are tracing that and it goes to the left, it's S. And if you're tracing that and it goes to the right, it's R. That's basically all it is. So the 4th group is oriented away as a dash, okay? And then so that's already like me looking at it on my paper, like top down, like right now on this document camera. 4 is oriented away. So if I'm tracing this like with my hands, so my right hand is 1, my head is 2, and my left hand is 3. So turning that is to the S, or to the left, and that's S. For this one, it's 1 up top, 1 is my head, 2 is my right hand, 3 is my left hand. Tracing that, that's going towards the right. That's R. Okay, let me see some of these questions.
So for this one, for B, we're now looking at the atomic number versus complexity, because like if you look at OH, like wouldn't that technically be more complex than F because it's 2 atoms?
I see. So it's this is something I'll say right now. So essentially, you look at the identity of each atom directly bonded to the chiral carbon. So first thing I see is fluorine, hydrogen, carbon, carbon. Okay, that's where you immediately are going to start classifying. Fluorine, hydrogen, carbons, and carbons. Out of those 4 substituents, do it based on atomic number, priority. So fluorine is higher than carbon, which is higher than hydrogen. Okay, so that gave me 1 and 4. Then I knew that. I had to look a little bit more careful. I keep getting these FaceTimes during the Zooms. I'm sorry. All right. So between 2 and 3, how do I know the difference between those? Is the right side of the ring has this extra group. The left side of the ring does not. Okay? so that's kind of like explaining it. I don't know. I'll catch you with more examples, okay? What time are we at? 12:54. I'm going to keep going with you guys because I didn't get to do as much as I wanted to, and it's important. So, because we're not going to have enough time to do it next week. Okay, so so we're going to be on 2C now. So we have this structure. We have this, and we have this. Okay, so quickly, carbon, carbon, hydrogen, fluorine. That's the first things I see, right? So out of all that, it's going to be 1 and 4. Like, that's the first thing. And then Q stands for carboxylic acid. So for all intents and purposes, you can draw it like that. Is this more complicated than that? Oh yeah, it's more complicated than that. Boom. Okay. Are you guys kind of seeing how fast it is? Like, it doesn't have to take that long.
I'm still a little confused on why the carboxylic acid is like less complex than the fluorine.
Okay. So the first thing you need to do is look at the atom that is directly attached to the chiral center. So this is clearly my chiral center. And when I'm looking at the atoms directly attached, it's going to be carbon, carbon, fluorine, hydrogen. Rank it right there. Out of those 4 atoms, I know that fluorine is the higher atomic number, so that's 1. Hydrogen is 4, and then something is going on with the 2 carbons. I need to look a little bit more closely to identify which one of those carbons is higher priority. And then from the carbon, you can do the next point of difference and see that it's oxygen versus a hydrogen, and the oxygen has a higher atomic number, so that makes it 2, and this 3. Or you can just take 2 seconds and look a step back and seeing, wow, this is crazier looking than this one. So it's 2 and 3. That makes sense.
Steven, I have a quick question.
Yeah.
So like, in the lecture, I could be wrong, but I remember she's saying that group 4 has to be in the back. So like, when we have to like rotate it and we'll like also change it, or like she also like, since 4 is in the front, we could just like reverse it. So like if it was S, then it becomes R. If it was R, it becomes S, right? Okay, I just wanted to make sure. Okay, yeah.
Yeah, exactly. So I was literally just going to do that right now. It's awesome that you got there.
Sorry.
No, you're good. Don't be sorry. It's awesome. Okay, so here we are. So essentially, trace the priority. Okay, remember, that's what we're doing. So 1, 2, and 3. When I do that, it looks like I'm going towards the right. So that seems R. But the one caveat was 4 has to be away in this just kind of steering wheel. Or like if I'm sitting by my side, like driving the wheel, like maybe, I don't know, something like that. This is a side view. 4, and you're looking down. So 4 has to be oriented away, always. So here, 4 is sticking out at me, okay? So you can just either, you know, if you're visual like me, I can see it. Like I can basically put my head like as if I was up behind this page, like behind here, and I could trace it that way and see that it's S. Or if you can just remember that if the wedge, if your 4th group is not oriented away, you just invert whatever letter you said. So if it was R, it goes to S. If it's S, it goes to R. Okay, so this one would definitely be an S configuration. But I could also just kind of like put my head underneath here, and I can see tracing it 1, 2, 3 from behind would give me S. Okay. 4 should always be a dash. That's correct. Do you mind explaining that again, Charles? Again, so you have to look at it. This is like how you assign, like this is the rules made by Kahn, Ingold, and Prelog. Don't yell at me, okay? So you have to number all your substituents. That's why you need to have a chiral center, okay? And there are 4 different substituents. And of those, 1, 2, and 3 top priority substituents, you have to trace those in a way where 4 is always oriented away. 4 always has to be away like this. So in this example, 4 is the dash. 4 is a dash. 4 is not a dash, 4 is a wedge. So that's where you have to just remember to invert whatever you assigned. Okay, I'll catch you on more examples. Exactly, I think you guys are explaining it, okay? So that was 2C, and now our last one is 2D, okay? So I'm shocked that some of you guys are saying you want your whole test to be this. Everyone hates these normally, like, so that's a good thing, I guess. We're talking about that chiral center. So quickly, let's number our substituents, okay? First thing I see is nitrogen, carbon, 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 okay? That doesn't tell me much besides knowing that this is number 1, okay? Then, is actually, I guess, see you, Leah. So that would be 4, okay? And the reason that's 4, and I'll explain in a second, is because here we have carbon, carbons, 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 carbons on the left and the right side of the ring. But what makes this side more complicated is the fact that we have an extra methyl, so it looks crazier. So this would be 2, and this would be 3. Okay, so again, 1, 2, 3, 4, that's how I assigned it. How did I know that? The first atoms that were attached to this chiral center is a nitrogen, a carbon, and a carbon. So that really just tells me 1. Then I look a little bit more closely. This substituent is just CH3. This one is a whole bunch of carbons in the ring. This one is a whole bunch of carbons in the ring. So this CH3 clearly has to be 4. Then from the left versus the right side, the left side has all these carbons and a methyl group. The right side has all these carbons and no methyl group. So I'm literally just doing it very like macroscopically. Like, what is it? Like, what am I looking at? Okay. Now, how do I trace this, okay, in such a way that 4 is oriented away? Well, 4 is already oriented away in this structure. So all I have to do is 1, 2, 3, and that's S, because it's this way, counterclockwise. All right. It's already oriented on the dash. All right, let's keep going. So I'm going to skip question 4 because 4 you can just do on your own. It's just an extension of 3, you know, doing it without the guided help. And now we're going to do page 43. Okay, so we're going to touch on enantiomers and diastereomers. And that's really where I wanted to end up today. So it's probably going to be another like 10 or 15 minutes if you guys want to hang out. I think it's worth it so that you guys can know this going into the weekend and you guys, you know, will be better off. All right. So we have built so far from the ground up. We know how to identify a chiral center. We know how to, you know, assign priority to that chiral center. We know how to assign chiral, achiral. You got it, Stephen. I love that. Anything for you. So you can basically, you know how to assign chiral centers. You know how to call something chiral, achiral, and/or meso. You know how to identify sigma planes. You know how to do. We learned a lot today. We really did. And the last thing we want to talk about is what happens when we have 2 of the same molecules but different RNS. So that's another type of isomerism that we haven't seen before. So for isomer, we have what we've already done. Now you guys will know connectivity. This is the end. We made it to the end. Connectivity meant constitutional. Okay. And then 3D space, we said, was 2 different types of things. So we have in 3D space, we can either have the rotations, okay, like rotating around bonds. So that's that signal. And we had 2 types. We had the chairs, okay, and we had Newmans. So I think you guys know where we're at so far. And then the next thing, so the other thing that happens in 3D space is chirality. Chirality. So that's RNS. So we have 2 different types, enantiomers and diastereomers, okay? And now we finally have basically finished this tree, okay? So we did this like 2 weeks ago. You know, we did this kind of last week, and now we're here. Okay, we're on the last branch of it. Okay, so hopefully you guys kind of know where we are. Okay, page up slightly. Yeah, you guys good? Thank you guys. You guys are sweet. Okay, so that's the point of these. It's like if you really can't make it to lecture, you can just watch these, and then you guys will be good too. All right, so enantiomers and diastereomers. So Caroline is back. She knew, she was waiting for me to do page 43, and now she's back. Hi, Caroline, welcome back. All right, so let's look at 5A, okay? So 5A says, draw the single enantiomer and any other diastereomer that there is. Okay, so what does that mean? So essentially, we're here, so we have this structure, enantiomer. The enantiomer is the specific name of a chiral center, or I'm sorry, an isomer, where all the chiral centers, every single one inverts, okay? So I know that was kind of crazy. So an enantiomer, what is that definition? Enantiomer means all CC's, chiral centers, invert, okay? Diastereomer, okay? Partial chiral centers, invert. So that's a very clear difference. Enantiomers, every single chiral center is going to be different. Diastereomers, let's say there's 5 chiral centers, maybe 1 inverts, maybe 2 inverts, maybe 3, but not all of them, okay? So that's kind of like just the key right there, okay? So 5A, it says, let's draw the enantiomer of this. Do you see do you see any chiral centers? Pause. Does anybody see any chiral centers? Yes, one. Yes. Okay, you see one. Great. I like that. That was specific. One. So if you see one chiral center, and that is a specific configuration, let's just say R, I'm just throwing that out there, then the next enantiomer structure has to be the exact same thing, but that chiral center has to be S, okay? How do I do that? It's so easy. You just draw this as a dash. Oh, it's a dash. That's it. You just invert literally the wedge to the dash or the dash to the wedge. And that quite literally changes your chirality. And I kind of alluded to that at the very, very beginning of looking with my hands. Like my left hand is built differently than my right hand, okay? So what does that mean? This hydroxyl group was built on the right side. This hydroxyl group was built on the left side. So by switching that building, you switch chirality or switch the handedness. So whatever this was, it goes to that one, okay? And the next thing I want to talk about is how many stereoisomers. This is always a good hint that you guys should know. Is something called 2 to the n. It's one of these common like exponential expressions that are very obvious in a lot of natural systems. But 2 to the n, it's an exponential growth factor. And it basically says is n is the number of chiral centers, right? So we have one chiral center, so that's 2 to the 1. 2 to the 1 is 2, okay? So that tells me there are 2 total structures I need to have. This is the first one, and this is my second one. Boom, that's a fact checker. Left Twix, right Twix. I love that. That's a great way of explaining it. Oh my God. That's great. I'm gonna look for a meme about that later. Left and right Twix. That's really great. Genius. It really is. All right. So that's an enantiomer. All right. And there's no diastereomers. Okay. So that do you guys kind of all follow that? There's just enantiomers here. So because I know that there should be 2 total structures, one was provided and one was drawn. So there can't be any diastereomers. So if you read the verbiage at the top of the page, it basically just says like, there's always going to be one enantiomer, and then there's always going to be like however many leftover diastereomers. Okay, and that makes sense because there's only one structure where all of them can invert. So there's always going to be one of these, and you could always have one or more of these. If that makes sense. So 5b. So we are here. So 2 to the n is the number of, yeah, you can go with number of isomers, but I like to just say number of structures overall. Okay, that helps me better. Cool, 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 cool. It's about to be cool in Gainesville soon. All right, so we're here. So how many chiral centers? 1, 2, okay? So 2 to the n tells me it's 2 to the 2, which means 4. I need 4 total structures, okay? 1 is already provided. So what is my enantiomer? My enantiomer is going to be the one where, nah, Steven is already cool. You're funny. So 5b. So there already is one structure. And we know how to draw the enantiomer. The enantiomer is pretty easy. It's just literally flipping all of the wedges and the dashes. So this is my enantiomer. Okay, because all of those chiral centers inverted. So this is my enantiomer I'll put here. And I need to draw 2 more. So probably, maybe let's do partial inversion. Let's instead of making, this, let's keep this wedge the same, and let's make this dash a wedge. So that's partial inversion. Notice I've only changed one of these. Okay, so that's a diastereomer. And then let me try the opposite. So let's keep this one the same and invert the other one. That's another diastereomer. So these are all 4 major 3D stereoisomers of this structure. But one thing you always need to keep in mind is you never, and this goes back to the constitutional isomers, you never draw the same thing twice. And out of A, B, and C, which 2 structures of A, B, and C are the same? B and C, okay, B and C, yeah. So the reason B and C is think about a pancake flip. So this is dash into the board, and you pancake flip that over, it's now the wedge. So here, my hands are curled in to indicate that those are going into the page. Pancake flipped. See how they're curling out? That's into the page. Now it's curling out. Ah, you see it. We love that. So it's curling in, pancake, wedge, boom. So these are the same. So you don't have to say these twice. Actually, it's frowned upon. Don't say them twice. You could just say that it's this one and it's meso as well. Okay, it's also a meso structure. Okay, and that's that. All right, so let's look at Please just do lectures. I like that. Thank you. I appreciate it. But listen, I learned everything I learned from Dr. Peterson. So you guys are at the same level that I was at. You guys can do that. All right. So let's look at don't be humble. You guys are sweet. All right. Let's go to let me see. Let's do 2D. Let's do 2D. I'm gonna leave you guys with C. I'm sorry, what was that? So is there two? So there are 4 total structures that exist, okay? That's what this formula tells you. You just have to use your brain. You can't be a robot, and you have to just remember that like you can't have 2 of the same thing, okay? And this is clearly the same thing. So yes, it exists, but we don't want you to draw both, if that makes sense. We know that there are 4 that exist, like I don't know. That's really what I'm just gonna say. Yeah, there you go. They do all exist, but just for the purposes of your class, just don't write 2 things at the same time, okay? Do we say 3 or 4? Okay, great question. If it asks you how many total stereoisomers exist, 2 to the n, always, 2 to the n, so you'll say 4, okay? If you're drawing, if you have to like pick from a set of structures, you know, maybe like it's a drop-down menu and you pick what structures match, in this situation, you would only pick A and B, okay? You wouldn't even be, I don't think, or I don't know how she would even do that on a multiple choice test. I'm trying to think, like, she might do it where like, these are like one option together. You know, I can see that, maybe trying to eliminate some confusion, but there's always 2 to the n, okay? So don't go down, don't just say 3, it's 2 to the n, okay? But if you're drawing these, which you're not really gonna do on paper for a paper test, I guess this isn't really an issue for you. Sorry, it's kind of weird when you're doing it on Zoom and stuff. I don't really know how they're gonna do it. All right. 2D real quick, so or 5D, whatever we're on. So we have this kind of bicyclic structure, so 2 cyclic structures, hydrogen, hydrogen, okay? And we wanna draw the enantiomer, okay? Really easy. First of all, how many chiral centers do I see? Okay, guys, put in that chat box. How many do I see? Tricky. 2, yeah, 2. So 1, 2, okay? So why are they 2? Again, we have this right side of the ring, this left side of the ring, this middle thing, and then this hydrogen. Like, it's very quick. Like, you'll get more comfortable making these determinations as you go, you know, you do practice. But I see 2. So that's 2 to the 2, which equals 4. And this is already one of them. So the enantiomer is really obvious. That's the enantiomer, okay? Then the diastereomer, remember, is partial inversion. So maybe let's keep the top one the same, but then we're gonna change maybe the bottom one. And then there's one more combo, and let's keep the bottom one the same and change the top one, okay? Is there a way, okay, let me do this. Out of, let's just see this. So out of A, B, and C, do you see duplicates? Does anybody see like duplicates? No. So yes to the duplicate question. B and C are the same, because if you were to rotate, again, this upwards, this like that. Oh, I'm sorry, wait. Am I not looking at this right? No, my bad. B and C are totally separate. I didn't see that. B and C are totally 2 separate things. There's no way that you can rotate this to get it to be the same thing. But A and the original are actually the same. So you would just say that this is the enantiomer of itself, and it's meso. So you could say meso, and this is the enantiomer. These are the same, so you wouldn't want to draw both of these. This is the enantiomer and meso, and these would be B and C, okay? So I don't really know, John, I don't really know if it's fair to say no enantiomers, because that is the enantiomer. Like, actually, yeah, no, you can say that. That's fair. That's fair. I like that. That's true. I just remember that. If your enantiomer structure is the same as your starting structure, there are none. John, that's great. Everybody follow what John just kind of said in the chat. If you draw an enantiomer structure and it is the exact same thing, notice it's a pancake flip. You just pancake flip it over. It is the exact same thing. So we can just basically come to the conclusion that there are no enantiomers. No enantiomers. And then these would be the diastereomers. Okay. Cool.
Stephen?
Mm-hmm.
Sorry to bother you, but just a quick question. I know like on the before you say to be as precise as possible. So
Uh-huh.
these, won't they be like geometric diastereomers, or am I wrong?
These would be geometric because they're rings specifically. They're not always going to be geometric, okay? But
Okay,
these specific ones are.
okay, that
Um,
makes sense.
yeah, and you'll see I didn't get to do this last part. There's going to be a subset, and that was probably towards the end of today, the geometric ones. So diastereomers can also be classified as geometric. So that's actually a great thing that you talked about. We're going to see that in a few minutes.
All right, thank you. Sorry
Yep.
to interrupt.
There you go. No. Why does meso mean in this context? Meso. Does it have chiral centers, and is there a plane of symmetry? It means the same thing across the board. Okay. Yep, that's right. Kelsey, that's great. Okay, so we're gonna move on to 6. Okay, so let me just tell you right now, this is all over this first test. Like, if you like, you need to know 6A through L. Like it's the back of your hand. You need to know how to do all of these and like have no issues. Like, this is guaranteed like stuff that's gonna be on there. This question. So you need to know this for sure. So now that you know all your different types of isomers, now we're going to be able to get a set of them and be able to determine what they are. Okay, so here's our first example, 6A. And I'll leave you guys in like literally a minute or two. I'm just gonna do one example. Okay, so we're here. And we're comparing it to that. Okay, so the first thing I look for is chiral centers. Okay, first thing I actually look for is, do they have the same molecular formula? Okay, and the same connectivity, because that's also, you can't forget about constitutional, even though it's very brief, like those exist. So no, these are definitely not constitutional. Clearly this is going to be a 3D thing. Okay, so stereoisomer. And I see that this dash went to a wedge, so that's inversion of configuration, but this wedge stayed a wedge. So if they stay the same, this is partial inversion. So only a partial, that's diastereomer. Okay. Now, something that we just kind of alluded, yay! Something that we just alluded to in the diastereomer category is there is this specific name, I know, there's always all these little details, named geometric, okay? And that is Cis Trans. So we've seen Cis Trans in other contexts, but now is really where it specifically comes about. And Cis Trans only happens with double bonds, or rings, di-substituted rings. Remember I said this? So we're looking for either double bonds, okay, where, you know, we could be trans or cis, which we've seen, or cyclic systems, where you could be wedge, okay, that's the cis one, or you could be wedge dash. So that would be like wedge dash, okay? So that's a specific subset. And now you might know why, like clearly that's partial inversion. So cis trans is just a specific name that we can give to these diastereomers, okay? So that comes up here. So yes, these are diastereomers, but specifically, you know, it's with respect to these two chiral substituents, okay, these di-substituted substituents, and one is on top, one is below, so that's the trans, and one is on top and one's on top, so that's the cis. So you could also say that these are geometric. So you could call this geometric diastereomers. Okay, geometric is the specific name. Geometric diastereomers. Okay, you guys get that? So if you think about the planar depiction of the ring, both wedges are above. Here, planar depiction of the ring, one is up and one is down. That's the trans. This would be cis, that would be trans. So cis, trans. Okay. 6B, okay? And I'm just gonna do a few more. I promise. Okay, 6B. Chiral centers. It looks like the wedges went to dashes, the wedges went to dashes. So I'm thinking enantiomers. Kelsey, you are so right. They're the same. They're not enantiomers. Why? Always double check. You can pancake flip this. Pancake flip that. So like we saw with, where's my model? Like, you know, for all intents and purposes, let's just say that this one methyl is the green. And then if you were to pancake flip it, doop, it's out. You see the pancake. We love that. So pancake, ready? In the back, oops, back, up front. Pancake flip it. Cool. So this would be the same or identical. And be careful. Like everyone, I spell identical, right? I spell identical. AL. Oh God. I know organic chemistry, but I can't spell. Same and identical. All right. So those would be the same. 6. I don't want to do C. C is a little bit hard, and I'm going to do one more. Let's see. We'll get to 16 maybe next time. Let's do 6G. That one's hard. Okay, so this isn't as obvious as just seeing, wedges changing to dashes, etc. Okay. Okay, and I think this is good for you guys to definitely practice on your own because this is a huge skill. So this is a little confusing for me to, really see what is what. Clearly, there's a chiral center. Okay, but the thing that I want to know is, are they enantiomers, are they diastereomers? And the way that I can do that is see what's the R and S configuration. Because if they invert, like let's say I assign R here and I assign S here and they inverted, that quickly tells me an enantiomer because there's only one center. So these tools, you can use them. Let's assign priority. So 1, 2, 3, 4. Okay, 4 is oriented up. So what you can do is put your head as if it was like under here, and you're like looking upwards, like you're looking up, like from below. Okay, so it's like a claw. Imagine like you're underneath the claw machine. And like you're one of those like stuffed animals and you're looking up at the claw. Okay, like I think that's like the best example I could give you. So, maybe in Newman fashion, if I'm doing it looking up like this, I'm getting that. Okay, so if you were to trace it, it is S. Okay, I'm looking down, like this bond. And this hydroxyl is clearly, oh, I'm sorry, I drew that wrong. So that would be 1, 2, 3, still same thing. So when you trace that, you get S. So clearly this is the S configuration. Okay. When you look at this one, we have same thing, 4, 1, 2, 3. Okay, so let's assign priority. Notice 4 is sticking out. So whatever this is, that's inverted. So 1, 2, 3 is R, but then don't forget to invert, it's S. So both are S, okay? So they're definitely not enantiomers, okay? They're definitely not diastereomers, so they are identical. Okay, so you have these tools that you can use to like determine, the chirality and see what's different here, and then the chirality was the same. So it's just a different depiction of it. We wrote it here. So again, it follows that rule of 4 always has to be oriented away. Okay, so if you were to look at it from above, that's like right in your face. That's the first thing you see, and that's not what you want. You always want 4 oriented away, and that is Kahn, Ingold's, and Prelog's thing. So don't yell. That's them. So it was like that example of let me find the paper of this. The driver, you're looking down as if 4 is like the cylinder that holds the steering wheel on it. Okay. So I think that's good for now. Definitely work through the ones that we haven't done. So we haven't done like a couple of these, and this is a huge skill that you guys need to know. When you're given a set, can you say, are they identical, diastereomers, geometric, like conformational, constitutional? You guys haven't learned Fisher's yet, so that's what I was planning on doing on Monday, and then wrapping up doing a massive review of critical thinking on Monday. So that's why I wanted to really get through all the material, and we definitely did. So all we have left to cover are Fisher projections, and we'll do all these like critical thinking problems on Monday. So just come into Monday like knowing everything already, and we're just gonna fine tune any like last minute details, okay? And I'll post all this stuff, I'll post all the videos, the remaining videos on Canvas this weekend. All right, good luck everybody.